Okay, hi, yeah, I'm Alex Binder. I am assistant professor in SUTD Singapore. And this is a talk about joint work with Grégoire, with Wojciech, with Sebastian over there. I named it on aspects of explaining neural network decisions with LRP. And LRP was just a term that we coined because we just need a title for the method. So, of course, why we want to have a predictions, because, all the people, they just train deep neural network models, and they predict, and they give nice scores. But often you don't really know what they really have learned, and you would try to understand it. In particular, we have done this before with bag-of-words models for HE stains of breast cancer. So you have the normal cells, nuclei, you have, fibrous tissue in between, and you want to kind of like find the cancer cells. But the funny thing about these methods is it's predictions trained on patches, on 100 times 100 pixels patches, where the cells are maybe something like 6 or 7 times 7. And still we are able to spatially resolve the evidence for and against cancer. So yellow-red is for and against cancer. Bluish is mostly lymphocytes and sometimes also fibroblasts. So in principle, this was already done with bag-of-words features. And of course, we asked ourselves, can we do this also with this cool and modern deep neural networks? And the idea of LRP is that given that we have a prediction over an input sample, we want to compute for every input dimension of this input sample kind of like a relevance score. And the idea was to decompose the prediction depending on the test sample. So, of course, you can think of this if you have a linear classifier, what relevance per dimension you want to have. Well, it's very simple. You just take, the weighted input. But it works also if you consider more complicated things like, old stuff, histogram intersection kernel SVM, but still works very well for small sample sizes. And the question is again, how do you want to decompose it? And again, you see it's nonlinear in the input, but it's still compositional in terms of sum over the input space, and you can just write down such a decomposition again. And of course, if you want to decompose a prediction function, you can have lots of trivial rules, right? The input for every dimension is just the prediction divided by the number of dimensions. Or I just assign the weight to a single dimension. So there are lots of non-plausible decompositions, and you need to impose additional constraints. And what are these additional constraints? So the first thing is I want to have a meaningful explanation for linear mappings, one that makes sense if I have really a simple linear model. It should be at least partially decomposable. So if you stack functions as you stack neurons and layers, you want to be able to apply this decomposition, kind of like element by element, and then top-down stack them together. And you can think of this if you have now a deep neural network. You initialize the output relevance. This is the prediction of your output. And in principle, you decompose this for every neuron separately. You start with those which are directly connected to the output. And you kind of like backpropagate the relevance scores. Okay, so there is more intuition behind that. So every neuron has a certain value of relevance, and we distribute the relevance top-down, okay, from a neuron to its inputs. And another idea that I had, that when you look up this 2011 patent on bag-of-words features, is the relevance kind of like should be conserved when you distribute it. And the other thing is that relevance was somehow related to a neuron firing or a neuron inhibiting, okay? So if you have inputs that stimulate a high output, you would imagine that it should have somehow positive relevance. Of course, if you think of this biological analogy, which really does not hold for neural networks, inputs can also inhibit it. Then you can think of either having a negative relevance or a zero relevance. This is a matter of modeling and of design choices. So in any case, whatever you want to assume, a larger input should get a larger share of the relevance. This was one of the major intuitions when we kind of like transferred version 1 from bag-of-words to neural networks, because kind of like a big input, either it affects a big activation or a big suppression. On the other thing, if you have a zero input in all those neural networks, okay, up to a bias, it does not do anything, it does not change much on the function value. Okay, so one idea behind this, you want to try to explain a difference relative to a state. Okay, so, and in principle, if you do classification, do standard thresholding, kind of like the zero output is kind of like the state of maximal uncertainty. If it's zero, you don't know, is it positive, is it negative? So if it's very positive, you have evidence for the presence of something. If it's very negative, you have evidence against the presence of something. And in the end, after thinking of this, you think that the relevance of an input should be something like a non-decreasing function of the weighted input. This was kind of like intuitions. Intuitions can guide you to design formulas. They can be 90% right and 10% wrong. Okay. And in principle, when you put all these inputs together and you want to assign them, in principle, to derive relevance for such a thing, which is in principle linear plus bias, affine, plus a nonlinear activation function, which is monotonically non-decreasing, then one ended up very quickly with two basic ideas for the relevance. Either it's the relevance of an input is proportional to the relevance of the output times the weighted input value, or what you can do is you can split this in a positive and negative part, and you can assign a different weight for the positive part of the input and for the negative part of the input. Okay, so these are functions that are either positive or zero or negative or zero. And once you apply all your constraints, for example, that relevance should be preserved, then you end up in deriving these formulas, which we have written up in the +1 paper. It's already 2 years ago. And then we tried it out at first on MNIST. It worked very nicely and very reasonably. And then we tried to take this to a pre-trained neural network. So we took a BVSC reference from CAFE. We implemented the layers. And here you see the results. And the interesting thing is about these results, you see that the relevance of an input pixel is not necessarily something like a gradient detector. Because what you can see, this is Borobudur, there is a very high sky gradient. It doesn't have much relevance for the prediction of a Stupa class. So, and it makes sense. It's more, like these architectural structures who catch lots of relevance on a Stupa class. Same for the cat. It's also very nice. So it's, how should I say, cat on similar colored background. It's more like the face of the cat that gets the relevance. Yeah, another example, it's frogs on similar background, a very crowded motorbike scene in Hanoi. It's also very nice. Again, there you have fat gradients, they don't appear. Okay, relevance really tries to measure, how should I say, how much does an input pixel contribute to the prediction? I don't say it's the only method possible, I don't say it's the best method possible, but it's our method. Of course, layer-wise relevance propagation is not the first idea, right? The first idea is that what you can think of is gradients, okay? So you compute the gradient and you measure something like a norm over the partial derivatives. And these are sensitivity-based approaches. There is a point when you think about this, they have a certain limitation. Namely, a gradient explains you how to make an image more or less a cat. Okay? It explains you the differential change, what you have to do to increase or decrease the score. It does not tell you what really makes up a cat and that. So this is a very simple example. So I have now a function, and then maybe the prediction boundary is here. But if I compute, how should I say, a gradient at the bump here, it will just point me in a totally irrelevant direction. And another thing is, if you look why gradients are not always optimal, consider just a simple linear case. This is what the norm of a gradient gives you. It ignores you, the sign of the input, and the strength of the input. It's really just a sensitivity. And okay, LRB was constructed to approximately retrieve this for both special cases. And you can see it also yourself, what gradients do. This motorbike scene is very typical. The gradient, in principle, has high relevance on the tar. It wants to add more and more motorbikes. It wants to increase the motorbike score by adding more and more motorbikes. And this makes sense for the gradient, but it doesn't make sense to explain why there is a motorbike in the image. Okay, in fact, if you think about this explanation relative to some point, you would come up more to something like Taylor decomposition. And indeed, LRP is related to Taylor decomposition, and Gregoire's talk later will explain this in much more depth. I try to see how much time I have. So, in principle, if you want to have such a linearization, right, Taylor decomposition does right that. But again, you see, you have to choose a point relative to which you explain. Same as LRP does. Okay, LRP by default explains relative to the zero state. But it's not a God-given choice, it's a design choice. So it's in principle, I will not talk too much about this because Gregoire will explain this in much more detail. We have a pattern recognition paper where in principle Gregoire took this to much more depth and applied the decomposition to the relevance function. Okay, that I said in principle already, right? There is in principle a choice of root and a choice of state relative to which you explain. This is in all the papers very implicitly, but you should be just aware of that, okay? That there is an explanation relative to a state always. Now let's go to talk about some applications of that and some extensions. There is one thing that does not fit very well in the structure of linear plus nonlinear activation, which is used in neural networks a lot. These are the so-called local renormalization layers. And the problem was, when we applied LRP, the beta formula was very nice, but the epsilon formula was super noisy. And of course, the point is, right, local renormalization layers, they do something with the input and produce a highly nonlinear output. So when we redistribute relevance from the output to the input, we have to take care of that. And just doing the identity like in the first choices, it was not a very good idea. And the idea that we follow this, well, we apply, because we want to have this linearization, we apply a Taylor decomposition. We have to be careful about choosing the root point, because if you choose the root point wrongly, you just get something like a diagonal Jacobian that doesn't help much. But if you take your input point, you use just some simple algebraic transformation, then it works well and better. And then you use this, and then you try out. So again, Caffe, either Caffe reference or GoogleNet, that wasn't Caffe. This was the identity in epsilon equal to 1. This is quite noisy. And if you apply then the Taylor decomposition also for the local renormalization layers, which follows the same philosophy of LRP, this becomes much cleaner. We did also an evaluation by perturbation methods. The technical details on how these work will be also explained not in my talk. And we found that whatever you do, we evaluated it on ImageNet, I think 10,000 images, MIT places, and we always found that in principle applying also the Taylor approach also to local renormalization layers improves, how should I say, the sensitivity of the computed heat maps. The point is, again, what I want to say is LRP is more a thinking principle. It's not a set of formulas. You can apply this not only within LRP. Of course, the idea, for example, to use this Taylor smoothing for local renormalization layers, you can use this as well also in combination with deconvolution. So for example, this is kind of like raw deconvolution, where you treat local renormalization layers as an identity. This is deconvolution. It's actually the L2 norm of it, because it gets the sign a bit wrong often, together with a Taylor smoothing. And you see it's not very well visible, but the image is much cleaner. Here you have much more kind of like grid artifacts outside of the snake. And by the way, this was also the way that we used the convolution in the TNNLS paper, because if I can use this trick for both methods, then I just try to elevate them on the same fairness level. Yeah, I still have roughly 10 minutes. This is good.
You have 5.
5, okay. I have 5 minutes, okay. This is okay. The heat maps, when you in principle redistribute relevance down to the pixel input neurons, they can be sometimes very, very sparse. And this can be sometimes not desired, but it can be cured. In principle, the idea is that from a certain level on, you redistribute your relevance not according to the rules, but you just redistribute it either flat or by the so-called V-square rule. And Sebastian Bach executed this very well and tried this idea very well out on the ICEP paper. And then you see this was a Pascal VOC classifier. You see kind of like dining table, and you see car, and you get the relevance more spatially distributed and not so overly sparse. Another thing is, in the last 5 minutes, you should think when you apply such things, do you want to have negative evidence or not? This is on MNIST, and on this MNIST task where you have a few number of classes and you have lots of geometrical constraints, negative evidence makes lots of sense. So this is the digit 3, and I compute the explanation for the digit 8. And what it says, I find lots of negative evidence because you should close the stroke there to make it an 8. In this case, for example, negative relevance makes sense. If you have something like a 1,000 class problem and you don't have a clear negative class like ImageNet, maybe then negative evidence is more a curse than a feature. Finally, let's go for one newer application of LRP. The idea was weakly supervised annotation of edges in images. So what is a problem statement? You have images and you want to label image edges with class labels. We focused on this on semantic boundary detection, which is a subproblem, which goes only for the outer edge pixels. The reason is just because there are not so many data sets with labeled edge pixels. And the reason is also why we tried LRP is getting a per image label is cheap. Getting a bounding box label is cheap. Annotating pixel by pixel on an edge is super pesky. And actually there is only SBD, only one real data set on that because of the cost of such labels. So the idea was, can we just use LRP to get approximate labels for image edges when we don't have pixel-wise labels for training, when we just have a classifier labeled on whole images. I just want to say there is another paper from the group of Bernd Schiele where they did a similar problem, but they tried on used already bounding box annotations. So we go here really by a whole image classifier, and we tried this out, and we wanted to see the performance of LRP without any post-processing tricks, so no intersection with grab cuts and things. And we measured average precision and maximal F-score. And what we saw is LRP performs better on this task than other methods that can use image labels, namely deconvolution gradient. Yeah, I'm almost done, it's good. But of course, if you can use pixel level labels and you use high for low, state-of-the-art deep learning, you are better. Clear thing, but they use pixel level labels. However, the before state-of-the-art methods, inverse detectors by Bharat Hariharan from, I think, 2011, is not so good, even though those used pixel level labels. So this is a very reasonable and formidable result, can be improved. We tried no post-processing tricks here. Of course, the question is, what limits the use of that? And the problem is that LRP, right, it puts lots of weight on internal edges. It makes no distinction, between internal and boundary edges. That's all. See here some results. And that's it.
So we have time for a few questions. So I have one. I'm not sure about, you explain quickly how you quantitatively measure whether a method for explanation is better than another one.
I think Wojciech is talking.
Wojciech will explain this in detail. So roughly, in principle, one can order regions by relevance scores in decreasing order, and then one can perturb them. in principle, according to this order, and one can measure the function prediction decrease. So, and if you have a method that magically finds the most sensitive regions, puts them first, you will have a very steep decrease. And of course, you do then some averaging tricks to get this numerically stable.
And do we have other questions for Alex? I don't see anyone. It was clear. So let's thank Alex again.